This is my Braun Oral-B Professional Care electric toothbrush. I bought it about, I don't know, a decade ago, and it already gave up on me. Yeah, the battery is shot, cannot hold enough charge for even, a single dental care session. So I guess we can take it apart, huh? This will probably be a prime example of German value engineering and production, because these thingies, they sell by the millions. It's the entry model from back then, but of course it has a lot of features. So yeah, contactless inductive charging or something like that. A blinking LED telling you that it needs to be charged. A blinking LED telling you that it is charging, and another very bright LED telling you that you are pressing too hard onto your teeth. Of course, there is no pressure or torque sensor in there. My best guess is they just measure the current through the motor, and if that exceeds a certain limit because of the torque, then they light up the LED. By the way, this is the replacement in stylish black and white, yeah, going with the times, and still the entry model. And of course, value engineering, they deleted that feature warning you about pressing too hard on your teeth. And they're still being made in Germany, and the newer one contains a nickel metal hydride battery. I guess the older one does too, but back then there was no requirement for that recycling mark here on the case. So I did a little bit of guesswork what we might find in here. Of course, we have that charger AC mains part, which will only contain, I guess, a single coil with some metal core. Yeah, in a construction like that. So the coil around a straight core and yeah, into that protrusion here. And then on the receiving end, yeah, where this sticks in, another coil around it. And that's your wireless charging. Okay. And that charges via a single diode. Yeah, no bridge rectifiers. If it takes twice as long to charge up, who cares? It's cheap. Charging up a 3-cell, 3.6 volt nickel metal hydride battery. And then, of course, we have a motor somewhere here with a gearbox. A freewheel diode, because this will be a brushed DC motor. And that is switched by some N-channel MOSFET on the low side. And I totally forgot, yeah, sorry to correct that here, not working. Yeah, you know, this is a line. Yeah, buy some custom chip, and there will also be a shunt resistor, I guess, so we can have some current sense for the over torque LED here. And yeah, the 3 LEDs are directly connected to our mystery chip here. So battery empty, charging, and motor, yeah, torque alert. We also need some kind of AC sense input, because we want to light up the charging LED. And yeah, of course, we need a power supply, VCC, which acts also as a DC sense input pin, so we know when the battery is full or the battery is empty, so we can control the battery and again the charging LED. And a ground connection. And that's it. That's my best guess. That's how I would build it. Getting this charging station apart will be a mess, because I guess everything is potted in there. Yeah. So yeah, I'll give it my best. Okay, I got nothing. So I guess I will cut it with a big saw off camera, just through it. So we have, yeah, at least a look inside. Big saw being a relative term, of course. Okay, I simply couldn't stop. It's like an itch, and you know you shouldn't scratch, but you do it anyway. Let's start with that side. So here's the big copper coil I promised you. But we also have here some other metal insert and a plastic insert. And this this is a PCB, and there's a part on it, as you can see, with big copper in it and some aluminium cooling stuff. We will see more of that on the other side. Are we in focus? Yeah, well enough. Yeah, there's the big core going in here that I promised you, our copper coil again, the plastic insert. I have no idea what that's for. I'll leave a comment. And the PCB. Yeah, and I guess this here is for cooling something on the PCB, like this part here. I mean, you don't have any air circulation, so if you are switching something like mains AC with a triac or something, you need a lot of metal to dissipate the heat. And yeah, it's really a PCB in here. Yeah, I destroyed most of it, of course, but here a resistor, here some other parts. And my best guess is they do a lot more than I suspected. So we saw there's something with a big aluminium heatsink here on the PCB, and that's probably a triac switching the main coil. And that little thingy here we saw with a little aluminium, maybe it is aluminium, it has also some copper traces in it. So I almost suspect this is a little sensing coil. And that senses when the magnetic field of that coil is disturbed, if power is sucked out of it. So I guess it switches on the main coil now and then to see if the device is sitting on the loading station. And if yes, it powers on the coil permanently. Oh, wow. German over-engineering, I guess. And yeah, the heatsink for that thingy, probably the sensing coil. I still don't know what this gap here is with another plastic filled in. Leave some hints in the comments below if you like. And yeah, the whole electronic that belongs to that control circuit. PCB again, the coil, and yeah, I already talked about that, the main core that I correctly predicted. So I correctly predicted, let's say, 10% of the circuitry inside here. That's not German value engineering, that's typical German over-engineering. Okay, let's continue with the main course. I hope this is not potted. Seems I've got more luck this time. So yeah, here's the receiver coil. I give you a close-up. There's also a spring inside. And that is pressing down here on the battery. And yeah, I will probably focus again down. Thank you. Yeah, I will reuse that receiver coil. Oh, I just broke one of the wires. Later on. I hope I can find it again. Need more tools. Tell you what, I will cut that open on both sides. There is no seam here, but yeah, there's something injected after assembly or during the assembly, and I cannot get it out. I think that the whole stuff is just, inserted, the whole assembly, until it sticks out here, and then they mold something in here. That came apart nicely for a change. I guess we can throw that away. Yeah. Here's the thingy for the tactile switch, which I, meanwhile, accidentally actuated. Still working a bit. Okay. We put that away for later because I still have, from my new one, a working loading station, and I guess we get the oscilloscope out. But yeah, later. For now, remember the spring and that thingy. I throw that all away now, including the rest of the loading station. And we take that thing here apart. We'll have a close-up on the, I call it, main board later on. For now, just let's try to remove stuff so we can easier access it. I can find my screwdriver. This is just snapped in, I guess. Yep. The gearbox, oh yeah, that's the motor, and only one cell. Only one cell. Okay, and this stuff here is also just, snapped on. Two connections here, two wires going to the motor, back and forth. That's, I guess, the warning LED, the big warning LED here. Okay, I already sacrificed them, obviously. But these fat thingies here, these are the motor connections. Just remember that for later. So this is the LED assembly. So these wires just run here zigzag down to the motherboard, to the LED connection, which was these two fat little solder bumps here. And yeah, the motor is directly soldered onto the board. This is a tactile switch here, or was it? Okay, it's dead now, obviously. So, more snap-ons. Okay, that's part of the tactile switch here, just going here to a ground connection, I guess. That's so... Oh, it's coming apart. They soldered that on, so we desolder it the quick way. Okay, and that's the motor assembly. And yeah, it's a brushed, can I have a focus up here? Just for a second. It's just a brushed DC motor. Oh, we'll go with that part here first. And this is spot welded into this metal frame. I don't know. Can we lever that open? Now I guess the motor should come free or not. More spot welding. This is really a feat of engineering. Or more snap-in. Nice access here. This can only be pressed in. Yeah. I can press that out. Wow. Okay, so that's the metal frame holding the motor and the gearbox together. Pinned with a rather massive pin here, if I might say so. Oh gosh. So that part on the motor is just helping the axle of that gear here. But again, here there are spot welds and but they can't possibly put them on after the fact, after assembly. Ah yeah, here. Snap in. Okay. This is all really wiggly because, yeah, there is a wiggly motion up here. The gear from the motor is driving this gear and then the front goes back and forth. And here comes the gear. And we have another spring. And that is the lever. This is the lever that makes the wiggly motion. Spring loaded. Can we pull that completely out? I already put the Dremel away. But I have still something to apply brute force. And this is rather massive. I'm really interested how they achieved the sealing because, I mean, this is used for years and no water ingress. Absolutely no water ingress. Yeah, let me work on that a little bit. Okay, I think I got it. It was just, you know, to lever out. And here we have the whole sealing. So a big very soft here, multi-phased rubber gland with some silicone goo on it. Yeah, because it's not rotating. So this flexible part here, when this oscillates here, this is just deforming. So really a completely sealed gland. Wow. There's nothing else in here, so I guess this goes to the wastebasket, and we still have here this little odd motor assembly with that plastic, with that frame here spot welded onto the motor. I don't think I can get that off. And here again, just, yeah, the wiggly parts that connected. So the motor is not connected in a very rigid fashion to that gear stuff, but really flexible. And I wonder if that is a magnet here. And the motor axis are really interesting. I mean, this is supported here by a wheel in that, yeah, spring-loaded assembly, just to take off some of some of the forces on the motor axis. This is okay. Made in Germany, engineered in Germany. No wonder the only thing... Oh, lost it or lost something. Oh no, I can't believe it. This might as well be a little ball bearing. At least it is a proper bearing. I don't know if there's are really balls behind that shield here, but yeah, maybe I crack it open. Give me a second. No, not really a ball bearing, but a proper bearing. This is unbelievable. Nothing much to say about the motor. There are no markings on it, but for Braun, okay, so they make that in-house. And a lot of more massive spot welding here. I won't bother with that. They just put on the frame on the motor and this plastic part to fit it to the gearbox. That leaves us with the intelligence here. So here comes in the two wires from the coil to these two solder blobs, and so the the cell is soldered to the board, but I already had my desoldering tool here, so yep, one snip, and the other side another snip. And this is a nickel metal hydride. We already saw this, FDK 1A800, so I guess American, no, not necessarily American manufacturer, because it has also Japan recycle and EU recycle. And it doesn't say which voltage. That's a bummer, but let's measure it. 1.29 volts, so I guess this is really just a single cell nickel metal hydride. Wow. Let's free the main board from the remaining stuff. Remember, that was a tactile switch, but by the way, there is another tactile switch here. I have no idea why. Maybe this was just a mass connection. Let me see, where's the on-on switch? No, the on-on switch, on-off switch is at the very top. So that was the on-on switch. I have no idea what that tactile switch is for, because there's nothing you could press. Huh, interesting. Maybe for another model? Who knows? Same mainboard for all models. Okay. So there's absolutely nothing here on the back side. And on the front side we have, yeah, the motor connectors and a ground connector for, or the connector for that tactile switch, and Yeah, that little thingy here is probably the MOSFET switching on and off, and there are no markings on here. Oh, there are markings there on the processor. Oh, I'll try to get that. The MOSFET driving the freewheeling diode. Then we have here resistor networks, probably for the LEDs, and another transistor. I suspect, I mean, here there should be two small LEDs on the board here, which go to, yeah, the indicator LEDs. And these are probably driven directly by the microcontroller, while the big LED, I remember it, other part of the housing, here, that was really bright when it flashed, and I find the LED, it's also a rather powerful LED. This is probably, and remember these were the LED pins switched by a little transistor, probably also a MOSFET. Then here comes the coil in, and this looks like a rather big diode, some trannies, and yeah, a controller. They have actually a battery loading circuit for that single nickel metal hydride cell on board here. Okay, yeah, you can do that. No markings. Oh, there might be markings here on that chip, but there are definitely markings here. If I'm not mistaken, that's an T44A, an ATtiny T44A. 4 kilobytes flash, 265 bytes EEPROM, 265 bytes RAM, runs from 1.8 to 5.5 volts at 4 megahertz. That begs the question, where do we get our 1.8 volts? So I'll have to correct my statement that this is probably a loading controller for the battery. I mean, the big capacitor here and so on. I don't see an inductor, but you never know. Maybe that's an inductor, but it looks like a diode. This might generate, and yeah, it's connected here. Traces. This might generate actually the 1.8 volts that's needed for the microcontroller. It reads OCM or 0CM. So even I couldn't find any information about that thingy just from the OCM marking. I found the inductor. Okay, so this is a step-up converter here. And I guess the rectifying diode must be built in. Because that diode here, that is directly connected to the coil. So this is, yeah, no bridge rectifier, just a single diode. Interesting. Okay, and I still know you cannot access that tactile switch here from the outside. And yeah, that was a MOSFET. Oh, there's also a marking on the MOSFET. Let's try to find that out. And the freewheeling diode here for the motor connections. We already talked about that. That's TSC 802. Well, let's try that. Yep, that's a 20 volt N-channel MOSFET with an RDS on of, wait for it, 65 milliohms at a gate voltage of 1.8 volts. Here, 1.8 volt supply voltage. I mean, really, 65 milliohms? at 1.8 volt gates voltage. Wow! But now let's have some fun with the coil and an intact, my new loading station. It gets better and better. With just the oscilloscope probes connected to the coil, and this is plugged in of course, I get these amplitude modulated chirps here of about 30 milliseconds. I cannot really trigger on it correctly, but that's the waveform. It's chirping. And look at it. That's a base frequency of about 74 kilohertz and amplitude ranging between 2, 4, 6, 8, between 4 and 8 volts, amplitude modulated. That's what that thing is putting out. Let's put a load resistor across the coil and see what changes. Okay, I connected a 100 ohm load resistor across the coil, and now we get aboutish 11 volts at 48 kilohertz. So it switched on, and as soon as I disconnect that resistor, switches off and goes back to chirping mode. Let me break out the calculator. So we're transmitting here basically, if I calculated it right, aboutish 1.2 watts, which is good enough to charge a nickel metal hydride battery slowly up. Maybe we can get more out of it. Nope. I don't think so, because the charging station is specified for 0.9 watts. I don't want to fry that thing by putting too big of a load on it. And that was, I think, the rather interesting teardown of a Braun Oral-B electric toothbrush. Made in Germany, totally over-engineered. You remember my initial idea how that thing looks inside? I was totally wrong. Totally wrong. Okay. Till next time. Bye.